Okay, so even though the word regression appears over here, it's misleading because the purpose of the logistic regression is actually to do classification. It's to do binary classification. Okay, meaning yes-no type of answer. Again, very similar to my diabetes example, given some data, does the person have diabetes or not? Or given some other medical data, does the person have cancer or not, right? So anytime there's a yes-no type of answer, 0-1 type, yes-no type of answer, that's called the binary classification. Okay, so logistic, I misspelled it, logistic regression. So how does it work? Okay, as you will see, what logistic regression does is, let's say we are given some data, and let me pick O's and X's. Something like this, right? And suppose once it's trained, your job is, given any data point, to tell you whether it's an O or an X. So once again, what we'll do is, through logistic regression, we'll come up with a decision boundary. Okay, so for example, as you can see visually, the decision boundary will be something like this. In logistic regression and plain logistic regression, the decision boundary is always a straight line. Okay, so okay, of course, for a two-dimensional data. For a 3D, 4D will become a hyperplane. Okay, so I have a paper. Okay, so in three-dimensional, for example, just like I have a surface over here, flat surface, so that will be a plane. So in 4-dimension, it will be, that's what we call a hyperplane, right? So logistic regression, first of all, can work in any number of dimensions, but it's always a linear separation between the two classes that we are trying to accomplish, right? Okay, so in logistic regression, like I said, the goal is the binary classification, right? So what we do is, to further give you the goal. So this is more like a statistical technique. Okay. So this is a statistical technique. Or at least the development of this, as you will see, is more based on statistics for optimizing classification decision based on given data. Okay, so in the statistical world, we have a concept of a hypothesis. Okay, so let's pretend what we have is we have n-dimensional data. Okay, so again, these are the features that we have for a given data. Just like height, weight, age, blood type, some other information. So we may have 4 features, we may have 10 features. So in general, let's pretend we have n features. So every data point will be an n-dimensional data, right? And suppose we represent that as x0 of I, x1 of I, xn of I. Or sorry, let me do it the other way. xi is the individual data, first feature, xi of 1, xn, xi of n. Okay, so those are the n features for ith data point as an example. Okay, so the hypothesis that we will form in this case will be, for example, beta 0 plus beta 1 of x0 plus let me start from 1, sorry. Let me, instead of 0 based, let me make it 1 based. Everything will come out a little better, otherwise, so suppose we do this, beta 2 of x2 plus beta n of x of n. So betas are our model parameters, as you can see over here. Okay, so given some data, meaning x1, x2, x3, and so on. Okay, so this is, again, you can do x of I, xi of, all right, let me not worry about it. But anyway, you get the idea. So our goal is, given some data, to determine what will be the optimal value of beta 0, beta 1, beta 2, and beta n, so that we can correctly classify, for example, the person has diabetes or not, or cancer or not, and so on, right? Okay, so because suppose we come up with, some betas for beta 0, some beta 1, beta 2, right? Because this is a statistical model or probability-based model, we want the output to always be between 0 and 1. Okay, so if we wanted to do that, what's easy function that if we pass a sigmoid, exactly. So if I define h of g of x for sigmoid over here, g for sigmoid, then I can basically go through a sigmoid over here, beta 0 plus beta 1 x1 plus beta n xn, right? Sigmoid, if you remember, as I mentioned to you, f of x, if it's a sigmoid, the equation is 1 over 1 plus e to the minus x, correct? So essentially, before I change it to sigmoid, let me express this in matrix form. So if I define two matrices, okay, suppose I define the beta matrix or the vector, beta vector, as beta 0, beta 1, beta n. Okay, and I define x as x1, x2.
Well, you need 1, x1, x2, so we
Oh yeah, I need 1, because this needs 1 more.
Yeah.
Okay, so then take a look at this equation. This, in matrix form, h of x could be written as beta transpose times x. Okay, so again, if you've forgotten, your linear algebra, transpose basically will change this to beta 0, beta 1, beta n, correct? So essentially 1 by n. And then if you take a look at 1x1, x2, xn, that's n by 1. So anytime we multiply matrices, Remember, the middle part has to match. 1 by n times n by 1 will give you 1 by 1. So you can easily see this will produce the same answer. Remember, we do row by column. So beta 0 times 1 will be beta 0. Beta 1 times x1 plus beta 1 times x1. So anyway, this equation is same as beta transpose times x, right? So if I have to write the sigmoid of it, I could write the exact equation for the sigmoid will be
Will be
1 over
1 plus e to the minus beta t transpose x.
beta transpose x, correct. Right? Okay, so that's the idea behind logistic regression. Why they call it logistic regression? Logistic is another name for the sigmoid function. So essentially, we are converting a linear model into a probability by passing it through a sigmoid function, right? Okay, so once we have this, now let me introduce another concept that we'll be needing as we go along. Okay, so rather than writing it as hg of x, because we'll always be passing through a sigmoid, let me just remove the hg. So anytime I write h of x, just again to keep having to write g, think of it this way. This is what we are trying to do, minus beta x. So I'll just basically think of sigmoid as implied. Okay, so now there's a concept called, so what we want to do is, so first let's define conditional probabilities for the two cases. For when class is equal to 1, meaning what category the data belongs to, and for when class equal to 0, right? So the way we write it in math is we will say probability y of I equal to 1. I is again one data, one person, for example, given some model. In our case, the model is, so given some input x and some model, betas are our parameters, so given, so this basically means in probability given, okay? So this will obviously be equal to h of x of I. Okay, so to understand this, what I wrote over here, think of it this way. Okay, suppose we've already trained, we know the values of the betas, whatever they are, 0.2, 0.1, -3, or whatever, right? Okay, somebody will give us some input. So this x of I further has many parts to it, x0, x1, xn of I, because it's an n-dimensional data, it's not just one value. So we multiply with the known coefficients, we come up with a number. We pass it through the sigmoid, so we'll get a number between 0 and 1, right? So what I'm saying is this will always be a number between 0 and 1. So obviously we want this value to be very close to 1 because we know the expected output is 1 in this case, right? Very similar. So this is essentially the probability, the actual probability when the expected output is supposed to be 1. Given the input, so given x of I, given whatever betas we already have trained. Very similarly, if you take a look at P, because remember, in a two-class problem again, so if I make some O's and x is over here. Okay, so this case was when the data given to us is of the x category, when the expected output is 1. What if the data given to us, unknown data given to us, belongs to the y equal to 0 category? So again, probability of yi, where the expected output is 0, given the input, given the model, what would this be? It should be, because see, then what will it produce? Will it produce a value, if it was doing a good job, close to 1 or close to 0?
So it's 1 minus.
1 minus, exactly. So you guys are learning it very nicely. Okay, so it would be 1 minus h of x minus I, right? So, so now what we'll do is we'll try to combine these two terms together. Okay, how do we combine these two terms together so that it doesn't matter what data is given to us, whether it's y equal to 1 or expected output equal to 0. So now we'll write it p of yi, given some xi, some data, given some model. Okay, see if you agree with this part. Okay, so this is an important equation. We'll be using it in a few other scenarios as well. See if it makes sense. So all I'm trying to do over here is combine both of these into one equation. Okay, let's see if this represents both of these. What if the expected output is 0?
0.
Then what will happen? Anything raised power 0 is what? 1. So this goes away.
Should it be multiplied?
I think it should be multiplied. So
Oh, sorry. You are right. There should be, I'm missing, sorry, yeah, you're right. That didn't make sense. It should be y of I,
like a step function.
h of x of I, raised power y of I. Don't forget.
You don't write that anymore.
It should be h of x of I. Okay, let me see. Did I make a mistake somewhere over here? 1 minus h of x of I. Okay, if y of I, okay, let's go to the two cases. If the expected output is 1, then this will reduce to h of x of I.
But then you have 0 again, and sum to the 0. It's 1. I think you also have to take out the exponent of 1 minus yi, multiply, not raised. Because if it is 1, then 1 minus 1 is 0,
Yeah,
so you get rid of that.
H times yi and 1 minus.
Yeah, it should be multiplied, sorry, not added, multiplied. Will that work now?
Yes.
Okay, if y is 1, then this will be just h of xi, and this is 1, so this will disappear,
Yeah.
right? If yi expected output is a 0, then you can see this is just multiplying by 1, and this is simply 1 minus h of xi, just like we had it over here. So yeah, so I made a mistake. It shouldn't be plus, it should be multiplied.
Oh, what I was saying is that you can have the plus, but then the exponents come down. So you have yi, h of x of I, plus 1 minus yi times 1 minus h of x of I.
Right, but
Both of this.
Yeah, this is okay. Yeah.
this is correct,
Yeah,
right?
that one.
Because this represents both of these cases. It doesn't matter whether you pick y equal to 1.
Yeah.
If you pick y equal to 1, this thing will reduce to just this part.
The 1, okay.
If you pick y equal to 0, this whole thing will reduce to just 1 minus h of x, right? Okay. So, so this is an important equation. Like I said, we'll be using it off and on, even in some of the other work. Okay. So then another concept which leads from this particular equation, and that concept is called maximum likelihood. Okay, so what we want to do is, so I, remember I is our basically ith training data. Okay, so if we knew, for example, again, diabetes example for 10,000 people, then I will be varying from, it will be one of those 10,000 persons, okay? So given one training data, so now suppose, like I said, if we are given, let's say, 10,000 training data, okay, then what we want to do is we want to maximize, because some of the data will belong to those cases where somebody has diabetes, some of them will be for those cases where there is no diabetes, right? So in that case, what we want to do is we want to maximize this probability, okay? So the way we write that is, let's say I equal to 0 to m, and pretend m is the size of the data, so m data points. Okay, and p of y of I given xi beta. Okay, which is obviously equal to I. Remember, this pi means these are being multiplied. So you pick the first training data, you compute the probability, so I equal to 0 to m, and this will be, so now let me put this right hand side over here. H of x of I, 1 minus y I, 1 minus y of I. Okay. So there's a small problem with this equation from a practical point of view. Okay, the probability, see h of x of I, as you can see, once again, is whatever data points were given to us, I mean whatever features were given to us, we multiply by the coefficients and pass it through a sigmoid. So h is the actual output of the network. Okay. What will be the typical value of this network if it's predicting correctly?
Close to 0 plus 1.
Close to 1, right? If it is predicting
Oh yeah,
correctly.
the lagging, yeah.
But if it is, there will be outliers in our data. So if it's predicting incorrectly, then what will be the value of this? Close to 0, right? So anytime we are given a lot of data, like 10,000 data, there will be some outliers, right? So as you can see, few values, or even if it's perfectly good data, what happens if you multiply 0.9 times 10,000 times, or 100,000 times? It will go to 0, right? So for this reason, we do not try to maximize the maximum likelihood. Okay, so because this can get close to 0, we do not try to maximize the likelihood. Instead, we try to maximize the log likelihood. Okay, so suppose I define my loss function, L of beta, as the log of the likelihood. Okay, which will be the log of I equal to 0 to m h of x of I 1 minus, oops, sorry, I made a mistake over here. This should be h of x of I minus h of x of I raised power 1 minus y. All right, so you guys remember from your basic math, what happens if I do log of A times B? Isn't it log of A plus log of B? And very similarly, log of A divided by B, right? So what will happen to this multiplication sign over here? Pi is, like I said, is the multiplication. So multiplication will change to summation, right? So this will, I forgot over here, there's a y over here. Okay, so see if you agree. So L of beta equal to log of the likelihood will become. Okay, so now let's go to the first term. Also remember from your basic math, log of A raised power B is what?
B log A.
B log A. Okay, so then what will this become? Okay, so take a look over here. yi log of h of xi. Okay, and then we're multiplying over here, right? So the multiplication will become plus. And then there's something of power to 1 minus yi log of 1 minus h of x of I. Okay, so this is called the log likelihood function. Okay, so remember h of x of I once again is what? Is the sigmoid of beta 0 plus beta 1 x1 plus beta n xn, correct? Or this is equal to 1 over 1 plus e to the minus beta transpose x of I. Okay, so think of it this way. Our goal is, what's our goal over here? Do we have to maximize this thing or minimize this thing?
Minimum. It's a cost.
No.
Maximum likely.
Okay, see, we started with, let's go over here.
Yes.
Do we want to maximize this probability or minimize it? Maximize it, right? So this is simply doing a multiplication of all the individuals.
Yes.
So obviously we still have to maximize it,
Yeah.
correct? Okay, then if we take, if we are maximizing some expression, taking a log of doesn't do anything.
Yes.
It simply is converting the multiplication to addition. Okay, so we still have to maximize this number, whatever the sum is. And by the way, now you can see, even though h of xi will be close to 1, right? Or 1 minus h of xi, if the model is correct. Doesn't matter even if we had 1 million things over here, the answer will be a finite answer. It will not go to 0, it will not go to infinity. So that's why in deep learning, 99% of the time, if we come up with a loss function, okay, which is a product of the individual predictions, we will convert it to a log likelihood so that the answer is meaningful, doesn't go to infinity or doesn't go to 0, right? Okay, so once again, goal over here is to find beta that maximizes the log likelihood, log of the likelihood. You guys agree?
Yes.
Okay, so now let me give you one more concept. In optimization theory, okay, maximization can be changed to minimization by putting a negative sign in the loss function. So in other words, what I'm trying to say is, rather than maximizing this number,
Just the negative.
if I say negative, then I'll be minimizing that number, right? Okay, so once again, majority of the time in deep learning or in the optimization world, we try to focus on the minimization, not the maximization. Okay, so essentially what I'm trying to say is, we will try to minimize the negative of the log likelihood. Okay, so our goal will be minimize the negative of log likelihood. Okay, so once again, all we do is, so there's another way to, because like I said, gradually I'd like you to understand the probability, the statistical part, the terminology, the mathematical terminology as we keep going, right? So, so our goal, if I have to express this goal over here, minimize negative of the likelihood, okay, but minimize under what condition? Whatever beta that produces the lowest answer, because we're interested in ultimately finding the parameter beta, right? Okay, so the way we write it in proper mathematical terminology is beta is the goal that we are trying to look for. We will say argmin of beta, L of beta. And what is L of beta? L of beta is this equation over here. So we use these terms like argmin, argmax. Again, think of it this way. You know, focus on to understand it better. Take a look at the min. So what are we saying? Minimize L of beta. When we say argmin of beta, then we are saying whatever minimum value was produced by adjusting the beta, give us that beta. And that is the beta which is our goal. This is what we want to find out. So now the next question, how will we find beta?